Hey everybody. Yesterday we started to look at the particle models of bond and thermal energy. The particle models of bond and thermal energy just use the behavior of individual particles to describe the way that large collections of particles behave. The particle model of bond energy turned out to be relatively simple. We just looked at how much energy a single bond between two particles would have, and then added that up for all the bonds in a substance. That gave us the total bond energy. But the particle model of thermal energy is a little bit more complicated, and it's going to take us a couple videos to put all the pieces together. Yesterday, I started teasing the ideas that we're going to introduce now. The ideas of modes and equipartition. A mode is just a box that thermal energy can go into. Each particle in a substance contains a certain amount of boxes. When you're adding thermal energy to the substance, you're putting energy into each of those individual boxes. The more particles you have, the more boxes that you have to put thermal energy into. This is the simpler part of this definition. What about the equipartition part? Well, equipartition just means equal partition. In other words, equally dividing up something. But what are we dividing up? Well, the answer turns out to be thermal energy. This is the thing that makes modes interesting. When we add thermal energy to a substance, that energy will always be split evenly between all of the modes in a substance. If, for example, you had a particle with 10 modes and you added some amount of thermal energy to that particle, 1/10 of that energy would go into each of the modes. If you had 10 particles, each of which had 10 modes, you would have 100 modes now. Any energy that you added to the substance would then be split evenly, 100 ways. This is the main idea of equipartition. And this is why the concept of modes can be really powerful if we're trying to understand thermal energy. Why does this happen? Well, a couple things to note here. First, this is an average. To say that every mode, every energy box in a substance always has the same amount of thermal energy is not exactly true. But think back to what we talked about last time. When we were talking about solids and liquids, we said that on average, half of our energy is going to go into kinetic energy and half of our energy is going to go into potential energy. When it comes to very large amounts of a substance, this average gives us pretty good results. So while it's true that each individual mode in a substance might have a slightly different amount of energy, and in principle, that amount of energy could be fluctuating, on average, every single mode will have the exact same amount of energy. Why this happens is not exactly super important. The reason comes down to quantum mechanics, which is a description of the way that the world works on very small scales. We don't have time to study that in this course. You'll see a little bit more of it if you take 7C. The important thing for our purposes is that this is an accurate description of the way that the world behaves. If you add thermal energy to a substance, that thermal energy will be split evenly between all of the modes in the substance. The more modes that a substance has, the more ways that this energy has to be split, and the less energy goes into each mode. The less energy that goes into each mode, the less the change in temperature. So we know that the amount of energy in each mode is going to be the same, but can we relate that amount of energy to temperature? It turns out that we can. If we know the temperature of a substance, we can immediately say how much energy is in each mode. That number is this number, 1/2 times the Boltzmann constant times the temperature. This hopefully seems reasonable given what we know about thermal energy. As the temperature of the substance goes up, the amount of energy in each mode goes up. As the temperature of the substance goes down, the amount of energy in each mode goes down. If we want to know the total thermal energy of a substance, we just need to take the temperature of the substance, find the amount of energy that's in each mode based on the equation, and then multiply that by the number of modes in the substance. It's exactly like when we found bond energy by computing the amount of energy that was in a single bond and then multiplying by the total number of bonds in the substance. This leads us to a really important question. How do we know how many modes a substance has? Well, this depends on two things. It depends on the number of modes that each particle in the substance has and the number of particles in the substance. The nice thing is that For a substance, the number of modes that each particle has will always be the same for all the particles. Once you compute it once, you just have to multiply that number by the number of particles in your substance to get the total number of modes. But how do we compute the number of modes? Well, there's three cases that we can think about here. We can think about solids, we can think about liquids, and we can think about gases. Solids and liquids are actually super easy. Every particle in a solid or liquid always has 6 modes. The reason is that solids or liquids always involve a bunch of bonds to the particles nearby. The individual particles just aren't free to move around wherever they want. The only freedom they have is the freedom to sort of vibrate back and forth. As we saw in the last video, when we add energy to a pair of particles, half of the energy goes into the kinetic energy of the particles as they vibrate, while half of it goes into the potential energy. Okay, so that's 2 boxes. Why 6? Well, the reason is actually because we live in a 3-dimensional world. Particles can vibrate in a bunch of different directions, but this vibration can always be broken down into 3 pieces. 1 front to back, 1 left to right, and 1 up and down. We live in a 3-dimensional world, so even if the particles have a ton of bonds, we can always simplify their vibration down to those 3 pieces. Each of those 3 pieces has a potential energy piece and a kinetic energy piece, and so we end up with 6 modes for solids and liquids. Now we can also see why for solids and liquids, the thermal energy of a pair of particles is split evenly between the kinetic energy and the potential energy. A particle in a substance will have 3 potential energy modes and 3 kinetic energy modes. By definition, each of those modes must always have the same amount of energy. And so the energy that we add to the substance gets split evenly between potential energy modes and kinetic energy modes. But what about gases? Gases turn out to be a little more complicated. Particles of gas are not bonded to each other, they're just floating around freely. When it comes to counting the number of modes for a particle of gas, we have to know a little bit more about the molecule itself and how it's laid out. You're going to learn how to count modes for gases in DL. I also made a video about this exact topic way back in spring of 2020. I'll link it down in the description. The nice thing is that there's just a recipe for counting the number of modes in a particle of gas. The number of modes depends on a few things, including how many atoms the molecule of gas has and what its shape is. Again, you'll see it in DL, and if you want more practice, I encourage you to check out the video that I've posted in the description. Now, let's step back and ask what all this information is useful for. We found that particles in a solid, liquid, or gas have something called modes. Modes are just boxes that thermal energy can go into. When you add thermal energy to a substance, it's always split evenly between all the boxes in the substance. The amount of energy in a box depends directly on its temperature. The less energy that a box has, the lower the temperature of a substance. The amount of energy is always exactly the same between all the boxes. If you think about this for a little bit, you might realize something interesting. If the temperature of a substance depends on the amount of energy in each of its modes, and the energy that we add to a system of particles is always split equally between all the modes, a substance with more modes, more boxes to put thermal energy into, is going to have a smaller change in temperature than a substance with less modes if we add the same amount of energy to both of them. This sounds like something that we've heard about before. It sounds like specific heat. Specific heat is just the number that describes how much energy we have to add to a certain amount of a substance in order to change its temperature. But specific heat has just been a number that we've been given. We haven't developed a model that allows us to understand where that number comes from. Until now, modes give us exactly the tools that we need to do this. If we know how to count the number of modes that a substance has, and we know that the number of modes affects the temperature change of the substance, we can come up with a model for specific heat. And that's what we'll be doing next time. That's all for this video. See you in the next one.